All right, so what I asked you to look at yesterday in those videos was in regards to the Pythagorean theorem, which is Pythagorean theorem. Okay, so a squared plus b squared equals c squared, right? Where a and b, seriously. Second.
You can do it. I believe in it. How was your weekend?
Good. There we go. All right, so this would be lowercase b. This would be lowercase a. That would be c, right? Okay. So what you learned yesterday, and obviously you probably didn't learn it yesterday. You probably knew this, right? That a squared plus b squared is equal to c squared, right? I like to write it using the symmetric property. I like to look at it this way: c squared is equal to a squared plus b squared. And you're going to hear me because it's easier. I think it flows better if you read it a squared plus b squared equals c squared. But in regards to like doing work and using ultimately the converse of the theorem, I think it makes sense to write c squared equals a squared plus b squared. I'll show you that here in a moment. But what we're saying there is if I give you any two of these components, you should be able to go through the algebra to solve for the third one, right? Okay. It's easiest to find c because then I don't have to do any subtraction or anything like that. I just sum things together. So let's say that I give you an example where this is 3 and that is 4. Okay, so c squared would look like 3 squared plus 4 squared, right? And then c squared would be, what's 3 squared? 9. 4 squared? 16. So c squared is equal to 25. C is equal to root 25, which is equal to the same thing as 5. All right, so that's how we would find c then, provided the two legs, right? So we call that a 3, 4, 5 triangle. It's a very important triangle to us. That's the smallest Pythagorean triple that we can come up with. Okay, meaning if you watch the video, talk about Pythagorean triple. Pythagorean triple is essentially 3 whole numbers who satisfy the Pythagorean theorem, and 3, 4, and 5 do that. Any multiple then of 3, 4, and 5 will also do that. So multiply those by 2, you get 6, 8, 10, right? What's 6 squared? 36. What's 8 squared? 64. If you add those together, you get 100, right? Which is the same thing as 10 squared. Okay. If I multiply 3, 4, 5 by 3, so I get 9, 12, and 15. That's a Pythagorean triple as well. Okay. There are other sets, but the 3, 4, 5 is the most useful. The reason that 3, 4, 5 is the most useful, a lot of times in construction, carpenters are interested in knowing right angles, right? People that do masonry, okay, bricklaying, stuff like that, they want to know right angles. So what they do a lot of times is that they will come over to the corner that they're interested in figuring out as a right angle, and they will measure out 3 feet on one wall. So if maybe they come out here to 3 feet and then make that mark there. On this wall, they'll come out maybe to 4 feet and make a mark right there. Then they're going to take their tape measure from here to there. And if it measures 5 feet, that angle right there is going to be what kind of angle? A right angle. If it's less than 5 feet, it's not a right angle. If it's less, think about this. If it's less than 5 feet, so that would mean this angle would have to be kind of come. These two things would have to come closer to one another, right? That way. So what kind of angle would that be? Acute. If it's more than 5 feet, that angle would open up more, which would make it obtuse. And that's why I think right now c squared equals a squared plus b squared in a moment is going to be nice for us. Yes.
So if you have like 6 as one of them and 8 as one of them?
I mean, it depends. So if this was 6 and that was 8, then yes, this would be 10. Okay, but well, what you asked is if one of those is 6 and one of them is 8, is the other one 10? So you didn't specify. So you could say if this is 6 and that's 8, is A going to be 10? No, because what is the largest value up there? What's going to be the log inside up there? The hypotenuse. Okay. So when I want to find A, this would be, I would go A squared plus B squared is equal to C squared. So A is unknown. C is 6, so square that, I get 36. 8 squared is 64. So now this is a situation where I've got to move that 36 over, right? So a squared is equal to 28. Okay. So then a, what two would be root 28? What two numbers divide 28? 4 and 7, right? Okay. So that would be 2 root 7 would be the length of a. So when we're dealing with, the reason I do that or give that example of your question is because it is important if we're going to check to see if something matches the Pythagorean theorem that we understand the hypotenuse always has to be the C, right? Or the longest value that's being provided. Okay. Now, if you told me that the legs both have to be 6 and 8, then yes, the other side has to, the hypotenuse automatically has to be 10. Okay. So here's kind of what some of the questions in the assignment dealt with. I think, guys, if I give you A and B, you should be able to find C. If I give you A and C, you should be able to find B. And you should be able to do those things, not so much off of what we did yesterday, but maybe the exposure you've had to it in the 8th grade and the 9th grade and so forth. Okay. Some of the questions that I think would be new to you would be maybe something like this, where I give you this side, let's say that side's 8. Let's say this side is 10. Let's figure out what let me give you a value for the third side. Now the third side, just based off of other geometry we've done so far in this course, the third side is either got to be between 2 and 18. Does that make sense? Remember adding the smallest two sides together and subtracting those will give you the range of the third side to make a triangle. So 2 and 18. So let's just choose a number. Let's go 16. Okay. My question now is that thing going to be a right triangle based off the information I give you? Well, if it is a right triangle, what equation should it satisfy? A squared plus B squared equals C squared. C being your hypotenuse, in this case being what number? 16. Sometimes you'll see them right this way. It'll say a triangle has 3 sides that are 10, 8, and 16. Is it a right triangle? Well, if it's a right triangle, what is the only value up there that could be the hypotenuse? 16. So whether they give it to you in a picture or they give it to you in words without the picture, you got to know that in order to be a squared plus b squared equals c squared, the c value has to be the largest number that they provide you with. Okay. So if I would have made this side here too, it's messed the picture up. What? It just all disappeared. So what was this? 8. 8. Did I say this was 10? If I make that 2, okay, or 2 point, let's make it 3 just to. Okay, so I make it 3. What angle now would I actually be checking to see if it's a right angle? It'd be A, right? A. Now it doesn't match the picture, but based on that information there, A would be the one I'm actually seeing if it's a right angle, because that's the one that's opposite the largest side. Does that make sense? Okay. But going back to, like I said, let's do the one where I had to uninstall and reinstall Smart Notebook, and it's not all configured the right way yet, so that's why I'm doing this stuff. So 8, 10, what did I say I wanted this to be? 16? 16. So let's go through and see if this is the right triangle or not. Okay, so we should see if c squared is equal to a squared plus b squared. So c squared would be 16 squared. Does that equal 8 squared plus 10 squared? What's 16 squared? 256. 8 squared is 64. 10 squared is 100. Do those two things equate? No, they don't. Okay, so can this be a right angle? No. Okay, so if it's not a right angle, like I said with that idea standing in the corner, if it's not a right angle, we should be able to say, well, then it's either obtuse or acute, right? Based off this information here, the way I determine whether it's obtuse or acute is I'm going to take c squared. If it's equal to a squared plus b squared, that is a right triangle. Okay? If c squared is greater than a squared, plus b squared, Greater than a squared plus b squared. What word, obtuse or acute, comes to mind when you see the word greater? Obtuse. I'm going to make this an obtuse triangle. If c squared is less than a squared plus b squared, what's it become? Obviously, it's got to be acute then. That's my only other option. Okay? That is the reason why I like to put c squared first. Because if I put a squared plus b squared first when I write these, let's take this first one here. Or sorry, this one here. If I write that as a squared plus b squared less than c squared, so that blue statement says the exact same thing that one says. But when I read it left to right, what's the word I say when I reach that inequality symbol? Less than. And less than, that word does not trigger to me, the way I view it, does not trigger the word obtuse to me. But when I read it as c squared is greater than a squared plus b squared, that triggers obtuse. Does that make sense? So it's just a way of trying to associate and to remember things. I think the best thing to do is write c squared first. Yes?
Do you want to put your name into the drawing?
No. No. All right. So that was the work that we did with the Pythagorean theorem. If we come across some examples that we need to see, we can do that. But my hope is that we already knew some of that stuff. Now I want to talk about where the Pythagorean theorem comes from. Okay? I want to talk about its development. So, would we agree that blue segment exists? Okay. Is that what we talked about in chapter 7? Yes. Okay. That's an altitude. Okay. This side here, I'm still going to call lowercase a. Let's call this lowercase b. The hypotenuse here, that distance, let's call c. Now, as we work through, we're gonna talk about that distance here in a moment. So let's call that e. Let's call that f. Excuse me. And the altitude, we're not going to use at all, so I'm not even going to label it. But when we look at that, do you guys remember from chapter 7, and hopefully we do, that triangle number 1 and triangle number 2 should be similar to the overall triangle? Okay, so let's write that similarity statement. Let's say the overall triangle is ABC, right? Okay. ABC is similar to triangle. If I go ABC, let's talk about triangle number 1. What angle do ABC and triangle number 1 have in common? A. Okay. In the two triangles, which angle is the right angle in ABC? Here it's ABC. Which one's the right angle in ABC? C. What's the right angle in triangle number 1? Yeah, I had to give you a point. Let's call that point D. So we take D, right? You lose. All right, so C and D need to match up. So we got that. And now what would be the middle letter for that? C, right? Does that make sense, everybody? So A, C, D, and A, B, C are similar. Can we do the same thing with triangle number 2 in the overall? Okay, so triangle number 2. Just kind of expediting this process. Doesn't angle B have to be the same? So they're both the second letter. D and C need to be the same. So the last letters. And then in this one here, the letter I'm missing would be D, right? Yep. Okay. Huh? What'd I do? All right, so let's start over. BD. BD would be those two, right? C is the right angle, D is the right angle, B and B match up, so I'm looking at C. Sorry. CBD. Is that right? Okay. So now, from those two things, can I create proportions? Can I create three ratios that are equal? All right, so let's say AB over AC is equal to BC over CD, which is equal to AC over AD. Okay? Let's talk about these bottom two. Let me do these in red. We can say AB over CB equals BC over BD equals AC over CD. Okay, and those are Those are what we talked about with similarity, right? Now, I'm going to go through there because I don't want to talk about the distance CD. I don't want to use this distance here in any of my proportions. So I'm just going to kind of wipe away that ratio because it has CD in it, so I don't want to use that one. And this one, I'm going to wipe that one away. When I wipe those away, look at the blue ones. I've got just a proportion now, right? Two ratios equal each other. The bottom red ones, I got two ratios equal each other, right? Now, I want to do some algebra with those. But the algebra I want to do with those does not really set itself up, or it's really not conducive with the values A, B, and AC. So let's go back and look at what AB is. So I'm going to take, doesn't fit well with, okay? It's not set up for, okay? So I'm going to look at AB. What's AB as a single value? What is AB called? It's called lowercase c, right? Does that make sense to everybody? So I'm going to replace that AB with C. What is AC? A to C is lowercase b. Okay, now let's look at AC. Well, it's lowercase b again, right? And AD is E. All right, so this is this last chapter. B is referred to as the what?
The geometric mean.
Geometric mean. So if I look at the geometric mean between those distances, I get B squared is equal to CE, right? Is everybody okay with that?
Yep.
All right, let's do a similar thing with the red. Okay, AB, what's AB? A to B is C. I'm looking at this set here. I'll get C over CB. What's CB? A. Over equals BC, which is still A, over BD. What's BD? BD is F. Okay. If I cross multiply, I get A squared is equal to CF. Is that okay with everybody?
Yep.
Okay. I'm going to erase this stuff because I'm running out of room. So I'm going to erase that stuff and bring all right, so we got those two equations. B squared equals CE, ignore that green mark, and A squared equals CF, right? I'm going to start with that blue equation. Would you guys agree that that blue equation is true, based on what we've just shown? B squared is equal to CE. If I want to take and manipulate that equation, let's say I want to add something to both sides of that equation. If I add something to the left-hand side, what do I have to do to the right-hand side? The same thing. Add the same amount, right? I'm going to add A squared to the left-hand side of this equation. So basically, I'm going to take this thing right here and add it with the B squared. If I want to add A squared to the left-hand side, I got to add A squared to the right-hand side, right? Okay. But I'm not going to put A squared over on that right-hand side. I'm going to put something that A squared is equivalent to. CF. Is that still adding the same thing to both sides? Okay. So when I do that, this sum over here on the left turns into A squared plus B squared. That's pretty familiar looking, right? The right-hand side, not C squared, it gives me CE. Keep messing this up. Gives me CE plus CF. That's not C squared, right? Or is it? What do both? This is the reason being proficient in your algebra is going to be useful, because it allows things to fall out of here that are going to make sense to us. If I see CE plus CF, what is in both of those terms? C. Can I do this? Can I write A squared plus B squared is equal to C times E plus F? I can factor that C out, right? Think about this. Unfactor. 4 that out. Distribute that back out. Does it give me C times E and C times F? Okay. So that is true. That's the same thing. But And here's the algebra part of it. This is why manipulating this way is useful. Look at your picture. What's another name of E plus F? By segment addition postulate, it's that distance right there, right? That's C. So let's replace this with C. A squared plus B squared equals C times C. Well, what's C times C? C squared. And that's where my formula for the Pythagorean theorem comes from. Stuff we already knew, right? Okay, yes?
Well, you see, the reason why I said no, I mean, I could have done the algebra, CE and CF, that doesn't look like C squared.
Right, but it is. But you see that it is C squared, right? Okay.
Well, I mean, not really. I mean, yes, if you use algebra and geometry, it is.
All right, well, we put in quotations on that. All right, so let's talk about another way of doing this.
You have to 2-year-old, dude. It doesn't. So you're a 2-year-old. No.
Well, I mean,
No.
what shape is that?
That's a quadrilateral.
Yeah, but it's a special type. Trapezoid, right? Anybody know the area formula for trapezoid?
B1 times B2 times H.
All right, do you remember this distance here? We talked about that being a mid-segment. Do you remember the length of it?
It's half. No.
Okay, so it's the average of the top and the bottom. Okay? So my tablet's not really working to write those values in here, but it's the average of the top and bottom. Do you guys know what the area of a rectangle is?
Yeah.
What?
1/2. No.
Length times width, right? Base times height, however you want to view it. I'm going to do this. I'm going to put a segment in right there. And we'll put a segment in right there. And we can do this for every single trapezoid we ever come across. What do you think that you see here with this triangle and this triangle up here?
Oh, they're right angles. No, they're vertical. They're showing a vertical angle.
Okay, they got that vertical angle. Okay, this H point is a midpoint, so that distance there is congruent to that distance there. This is congruent to that. These two triangles are congruent. Okay, so what I'm going to do to figure out the area formula for a trapezoid is I'm going to cut this triangle off, and I'm going to slide it up here and paste it on right there. Does that make sense?
You're going to make a rectangle.
And I can do the same thing over here on this side. And what happens is does everybody see this rectangle from K to J to L to M back to K? Well, that rectangle is made up of the same components that the trapezoid is made up of, right? And they're just cut up and repositioned. So the area should still be the same, right?
Yes.
Take your desk and cut it up into 30 pieces and move them around and reconfigure them. It's still the same exact area that your desk is. Does that make sense?
Mm-hmm.
So that's what we're doing here. The area of that rectangle is base times height, right? Or length times width. Well, this length right here, this length from J to L, is that the same thing as H to I? H to I was the mid-segment, right? You told me that's 1/2 B1 plus B2. Okay. This distance here is the altitude or the height of our trapezoid. So what we get, I'm going to write this formula up there in a moment. We get the area of a trapezoid to be 1/2 H B1 plus B2. All right. Now, I would have liked us to already have known that. Okay, maybe not where it came from, but maybe the formula. Because this is what I want to do. I want to take that triangle right there, and I'm going to create a second triangle that is identical to it. So it's 1, 2, 3, 4, 5, 6 by 2. So 1, 2, 3, 4, 5, 6 by 2. I get that triangle there. Does that make sense?
Yep.
Okay, so those two triangles are the same. I'm also going to put in that segment right there. What did I just create? Okay, so I've got 3 triangles, but what is that shape right there? Trapezoid. Okay. Huh? All right, so here, let's do this. Let's identify some parts here. If I identify some parts, let's call... actually, let's do it this way. Because of the letters I've used. This would be A, right? Across from angle A would be lowercase a. If I rotate, so these two triangles are the same. So this would be A, and that there would be B, correct? Make sense? This would be C. That would be C. Now, I'm interested in figuring out what this angle is right here. And we'll talk about why we had to find that angle here in a little bit. Actually, let's just go through and find the area of this trapezoid, trapezoid first. Then we'll come back and talk about that angle. So if I'm talking about this trapezoid, okay, formula for the area of a trapezoid is 1/2 base 1 plus base 2 times the altitude h. Okay? So let's look at this figure I have in front of us and figure out those parts. What would h be? H is going to be the altitude, that distance right there. What would you call that? B plus A. Does everybody see that? Okay, be those two distances add together. So I'm going to say I have 1/2 h is going to be B plus A. Okay? Now, B1 plus B2, your bases are that one and that one. What do I get if I add those together? Huh?
Are we going on different letters or the values?
Just the letters. The lowercase, I mean, they are values, but we just don't know what they are, right? It'd be A plus B, right? Or B plus A, it doesn't matter. Okay, but it's that right there would be the area of that trapezoid based off of that formula for an area of a trapezoid. Does that make sense, everybody? What's another way I can find the area of that figure without having to know anything about trapezoids? What's that figure comprised of? What's it made up of? Triangles. Do I know that area formula for a triangle?
You do.
Why don't you know the area formula? Our area of a triangle is 1/2 base times height. Okay? Now, when we talk about base and height, they have to be perpendicular distances, and that's why I like these to be right triangles. My base in that triangle number 1 would be A. My height would be B. Does that make sense? So I get 1/2 A times B. Okay, so that's triangle number 1. Look at triangle number 2. What was the relationship between triangle number 1 and triangle number 2? They're congruent. Okay, so triangle number 2 would be, triangle number 1, it'd be 1/2 AB again. Now, finding triangle number 3, area triangle number 3, figuring that out it'd be this triangle here. In order to make it convenient, I would need to know what kind of triangle that is. I need to know what kind of angle that is right there. Does anybody know, you should, the relationship between that angle there and that angle there? No. What do they add up to? 90. Okay, the acute angles of a right triangle are complementary. So, and I don't know which one's which, but let's say that this one here is, I'm going to use a Greek letter theta. So let's say that's theta. Wouldn't this be 90 minus that? And theta is just like a variable like x. Does that make sense? Okay, just usually when we use Greek letters, we're talking about angles. So theta and 90 minus theta. If I look at this angle right here, what's that angle right there going to be?
That's going to be the 90 minus
Yeah, that angle there is the same as that one down there, right? I'm looking for this one. Let's call that one alpha. What should this red angle here, this alpha, and this theta add up to? 180. So let's see. If we come over to the side, let's do it up here. We go, 90 minus theta, which is this one, plus alpha, plus then theta, should equal 180. What happens to these two thetas? They cancel out, right? So I got 90 plus alpha equals 180. What's alpha? 90. So that guarantees that that's a right angle. Why do I like that? Because now I know C is a leg or a base, and C is also a height, right? Does that make sense? So I go 1/2 C times C to be that area. Is that doable?
I can't tell if alpha is the alpha symbol is supposed to look like an A or supposed to look like a fish drawn by a child.
Fish drawn by a child. But it represents A. All right, so this is the area one way. If I add that, and that together, it's the area a second way, right? What do you know about those two areas? They should be the same. So let's write this. Let's go 1/2 A plus B times A plus B. That's this one. Should equal 1/2 AB plus 1/2 AB plus 1/2 C squared, right? Is that okay with everybody? Yeah. All right. How can I get rid of those 1/2s? Times everything by 2. So I'd have A plus B times A plus B is equal to AB plus AB plus C squared, right? What's A plus B times A plus B? What's that tell me I have to do? I have to FOIL. Okay? So I'm going to FOIL left-hand side. It gives me A times A gives me A squared. A times B gives me AB. B times A gives me AB. B times B gives me B squared. And then I've got AB plus AB plus C squared over here, right? What's going to happen with that AB and that AB? Cancel. What's happening with that AB and that AB? Cancel. When they cancel, what are you left with? And then A, B, and C are that thing, and that thing from the original right triangle. So it relates those 3 original parts correctly. Does that make sense? All right. So those are 2 proofs for the Pythagorean theorem. There are, I believe, approximately 79 different ways to prove the Pythagorean theorem to be true. 79, validated reasons. Okay. Now, what I want to do just briefly in the next 10 minutes is talk about a special type of right triangle Pythagorean theorem. That makes absolutely no sense. Think about what you just said. Yes.
Okay, so why would people need 79 different ways to prove it? Why not just 4 or 5?
Well, why even that?
Why
isn't 1 just okay?
Because you gotta make sure. Why do you even need 1? Yeah. Why do we need math? Why do we need math? Okay. Fine.
Why do we need math? Seriously? All right. What kind of triangle is that?
That's a right triangle.
It's a right. Think about what you just said. That's the dumbest thing ever. That might trump his stupid comment.
I don't know. I'm kidding.
How can it be right? How can it be right? Did you say right what?
I'm kidding.
Okay.
No, you're right.
All right. So it's a right isosceles, isn't it?
Yeah.
Okay. Another word for right isosceles, another phrase, is that it's a 45, 45, 90 right triangle. Okay. Right angle, that's 45 degrees. That's 45 degrees, right? You're going to hear me talk about both those, okay? Now, if it's 45, 45, 90, or it's isosceles, what's that tell you about both legs? They're equal. If I call that leg in and that leg in, do we have the ability to solve for C? Okay, let's do so. So I'm just choosing arbitrary values of n. They're random. They could both be 2, they could be 3, they could be 5. What I'm doing here is creating a formula that says no matter what your leg is, this is how you can find the hypotenuse in a 45, 45, 90. Pythagoras says you could take C squared plus n squared, right? C squared is equal to A squared plus B squared. It's just case the A and B are the same thing. Does that give me C squared is equal to 2 n squareds? Do I ever solve for C squared or do I solve for C? Solve for C. So I get that, right? Now, can I break that apart this way? That make sense? It's a product. 2 and n squared can be multiplied in either order, right? Okay, so 2 times 25 or 25 times 2 is still the same product. And then because they're square root, it's a product under a square root, I can separate them. So now what's the square root of n squared? N, and then I have radical 2, right? So it tells me that this distance here, this C value, this hypotenuse, is always in radical 2 when I have side lengths that are in. So what's nice about that, what if this side here was 3, that side was 3, what is this side here? What's my hypotenuse going to be? 3 times square root of 2. Now, yesterday in your homework, there was a question that asked you to do this. It gave you 3, 3, and asked you to find C, but it's asking you to do it this way. 3 squared plus 3 squared is equal to C squared. Get 9 plus 9 is equal to C squared. 18 is equal to c squared. Square root of 18 is equal to c. And then I think, well, that's 3 radical 2 to get c, right? I go through that entire process. Well, that entire process is what we did just right there. So why do it over and over and over and over again for every new problem? If I know it's a 45, 45, 90 triangle, whatever they give me as my leg, the hypotenuse is that times radical 2. That's a theorem that says every hypotenuse of a 45, 45, 90 triangle is radical 2 times as big as a leg. Okay? So what I think is beneficial, you hear me say this all the time, I want to talk about this being a template. Okay? So let me just clean that up. A template means, like you guys have opened up PowerPoint and there's already predefined templates that allow you to plug in like pictures and text and that kind of stuff, right? Okay. So that's a template that we're going to use to do every one of these problems that we come across. Now, the triangles that I mess around with or that we use might not be the same size. Our template is able to, because we don't know what n is, our template is able to grow or shrink however we need it to. So let's say I've got this right triangle. Let's say it's a 45, 45, 90. So that shows me 45, 45, 90. Let's say this side here is 6 and 6. If I'm able to allow this black triangle to grow, and we'll lay it right on top of my red one, what would n match up to? N and 6 would match up, and they'd be congruent. If these two triangles end up being congruent, those two distances would be what to one another? Not distances. The segments would be congruent. The distances would be equal. Okay? So we would have n on top of 6. We get an equation, n equals 6. So now that I know what n is, can I use that everywhere else in the picture? If that's 6, this is 6, what's my hypotenuse? 6 radical 2. I plug that n in right there, and it gives me 6 radical 2. Is that something we can do? What if I do this? What if I say this hypotenuse is 5 radical 2? Okay, so I match my two triangles up, right? What would overlap? That and that would lay on top of each other, right? That tells me if they're congruent. That tells me that those are equal. So I have n radical 2 is equal to 5 radical 2. Now, bear with me on the algebra here, because I want you to learn the algebra. That's a one-to-one correspondence in the equation. Meaning, if I'm going to get the left-hand side to be identical to the right-hand side, what does n have to be? N has to be 5, right? That's the only way those two things become visually the same. But the algebra says this is a, what kind of number, or what do we call the number out in front of a variable? If I have 3x, what's the 3 called? Coefficient, right? Radical 2 is a coefficient. It's 1.4, 1.4, whatever, forever. Okay, it doesn't terminate, doesn't repeat. So we have to write it as that symbol, but it's still a coefficient. And we write it at the end because this, if I write it, or sorry, I write the variable up front, because if I write it that way, sometimes people get sloppy with their handwriting and do that. And radical 2 times n is different than radical 2n. Does that make sense? So we write it out front, but it's just a coefficient. So if I want to try to isolate this n, I do what? Divide by my coefficient of radical 2. So that goes away, gives me n. Come over here, divide by radical 2. What's it leave me with? 5. And that's the algebra to verify that, yeah, I just match up the n radical 2 and the 5 radical 2 and say, what does n have to be? It has to be 5. Does that make sense? Now, why do I want to do that? Because this is what's going to happen. Let's say if this side here is 6, where the radical 2 has already been multiplied through and it equated to 6. So now if I match these two triangles up, I get n radical 2 is equal to 6, right? Well, what was the algebra down here? What did I have to divide by? Radical 2. So let's divide by radical 2. So I get n, those are going to cancel, is equal to 6 over root 2. Do I like that root 2 in the denominator? What do I have to multiply by? Radical 2 over radical 2. Okay. So what's the top become? 6 radical 2. What's the bottom become? 2. Okay. Is that the same thing as 6 over 2 times root 2 over 1? I multiply those two fractions, so I get the same 6 radical 2 over 2. So what's that telling me then? What's 6 over 2 the same as? What's that the same as? 3. So it tells me these two things cancel to give me 3. And 3 radical 2 then is the n we just solved for n, so that's that side right there, and that side right there. Because if I square those and add them together, I get 6 back. Okay? I think those are the harder versions. Obviously, if I give you n to be 5, you know 5 radical 2, right? You get n to be 12, you know 12 radical 2 is my hypotenuse, right? If I give you my hypotenuse is 5 radical 2, you know n is 5. If I give it to you to be 7 radical 2, you know n is 7, right? But if I give it to you as 6 or 12 or 30 or something like that, we got to go through that algebra to figure out what n is, okay? If you think about it, if you do enough of these, you'll see a pattern. But I want you to know the algebra before I tell you what the pattern is. There's assignment over 8.2. 8.2 is going to be done in several days. So that was day 1. Give you an assignment over just these triangles. I'm going to leave it open until Friday. Okay? If school's canceled tomorrow, be in your email for blizzard bag number 2.